Right here we have the crab nebula, which sends out energetic pulses 30 times a second. So I've chosen that as my iconic image of the pulsating universe. And here, of course, we have the aurora borealis, which is the electric current coming into the Earth. So that's my symbol of how planet Earth is affected. So there are discharge events occurring all the time on all kinds of scales, on a whole range of scales in the cosmos. This one is 30 times a second. Here we have a supernova remnant. So there was a supernova which sent out a tremendous burst of energy when it happened. And here we have even larger scale. This is a stellar nursery. So we have a cathode object here, which is being impacted by a incoming current, and every one of those strands is creating stars. So that's a huge scale discharge event. And all of these discharge events are sending spikes of energy down galactic currents. Whatever current they're on gets a spike of energy whenever there's an event like that. And those energy spikes reach planet Earth. Here is an image, here's Don Scott's image of the Birkeland current that powers the sun. So that current is going to get its share of energy spikes. And then those are passed on to the Earth proportionally. So the current coming into the Earth is a spiky current. It's not a constant current. It's going to get spikes whenever there's a discharge event that is connected to our circuit. And that's going to cause heating. So the reason we see the aurora borealis is because the ionosphere is being heated to glow mode. In this particular report from Themis, they call it 100,000 amps circuit coming in, and I think on an earlier talk it was an even larger amount of amps. Doesn't really matter, it's a lot of amps. That's what we care about. And it's not just I call this the entire ionosphere. I suppose I should call it the plasmasphere. But the Van Allen belts, these radiation belts, that's because of current flowing through them. And that's being heated. Plus the atmosphere is being heated by discharge from the ionosphere to the surface. It's like a 250,000 volt difference between the ionosphere and the surface. And these weather events are discharge across that potential. So the whole Earth system is being heated by the current that flows through it. The Earth is basically a resistor for the current, and resistors heat up. And it's proportional to the current flow, so that an energy spike is going to create a heating spike. So there's no question that the Earth is heated electrically. The question is, how significant is that heating? So to get a handle on whether that has any significance to it, let's take a look at the climate record. So what we have here is the last 400,000 years as recorded in the ice cores in Antarctica, in Vostok. I just downloaded this data from the official website and charted it out. So what we see is about every 100,000 years, there's a major spike and that's how ice ages are ended. And then we see little spikes about every 10,000 years. So basically, the temperature record is nothing but spikes. There's no level periods, it's all spikes. And they occur on a cyclical pattern. So let's look at this, let's talk about climate a little bit while we have this slide here. The Earth is 90% of the time is in what we call an ice age. It's unusual to have an interglacial period. So ice ages are normal. And when we think about ice ages, we think about people wearing skins, hunting mastodons, woolly mammoths. Well, that's not what ice ages are like. a lot of the northern hemisphere is covered with glaciers, but that doesn't mean the Earth is cold. I mean, the difference between an ice age and a non-ice age is only 10 degrees. A place like Phoenix would be much more livable if it was 10 degrees cooler. And also, because all the water is taken up in the glaciers, the sea level is about 200 meters lower, which means that what we call the continental shelf becomes the shoreline. So in the tropics, it's more livable and there's a lot more land. So an ice age isn't really that the Earth is cold, it's just it's colder. But there's nothing to prevent life or agriculture or civilization or anything else during what we call an ice age. So actually, ice age is the normal, and an interglacial period is a crisis time because of this huge energy spike which ends it. And suddenly then all the glaciers are melting, which means tsunamis all over the world. I should see what's next here. Right, okay, so now what we're going to do is we're going to zoom in on the interglacial period. So we're zooming in on this little part here, and what do we see? More spikes. So the heating pattern of the Earth is a spiky fractal pattern. We're having spikes at all scales, and that's what a fractal pattern is. It's a very distinctive, it's not random. It's not at all random. It's a very distinctive, non-random pattern of cyclical spikes. So what we have practical energy spikes from the cosmos and practical heating spikes in the temperature record. So basically we have a unique fingerprint match between heating caused by discharge events in the cosmos. So we have a pattern match, but we don't know about the magnitude. I mean, it conceivably could be a coincidence that the patterns are the same. So what we need is some direct evidence. Is there any direct evidence for an electrical effect on climate? And there is, thanks to Ben Davidson, because he showed that solar activity, variations in solar activity, are strongly correlated with significant climate change. And variations in solar activity are, of course, due to fluctuations in the current that powers the sun, which is proportional to the current that comes into the Earth. So my hypothesis then is that climate variation is due to fluctuations in the current flowing into the ionosphere. Now, I really should say it's current flowing into the Earth system. So it's not just the ionosphere, it's the whole Earth system. And I think it's I've given a very sketchy rendition of this, but I think it's a strong hypothesis. But I think if this is what causes climate variation, of course that's interesting to know how something works. But what's even more interesting is the implications of the hypothesis. Here's the first implication is that we have a seismograph, basically, or a voltage graph of discharge activity into the past. So this is a new window onto the cosmos. We can learn things from this that we couldn't learn any other way. And in particular, let's take a couple. There we go. We can look for correlations between heating spikes in the record and things that we can see astronomically, like the Crab Nebula, which was a pulsar. It's a supernova remnant. And we know from records that were kept that occurred in 1054 AD. Well, that exactly matches one of our spikes. So what that would indicate is that the spike of energy that caused the supernova was the same spike that caused the heating spike on the Earth. Because you think, what causes a supernova? Well, supernova happens when the double layers break down. What's going to break down the double layers is going to be a surge of current which overloads them. It's just like a circuit breaker or a fuse. If you put too much current through it, it goes. And then here we have the Vela supernova remnant, which astronomers tell us happened 12,000 years ago, which is the spike that ended the last ice age. So again, of course you might say, well, actually, it didn't occur 12,000 years ago. The light got to us 12,000 years ago. Well, what that's saying is that the voltage spike got to us at about light speed, at the same time the light did. Now, so that was one implication of the hypothesis, is that we have this record of this window onto the cosmos, that's basically like a seismograph. There. The second implication of the hypothesis is that discharges seem to be always cyclical. Now we know with pulsars that the discharges are cyclical, but because it happens in fast enough that we can observe it, but we would have no way of guessing that 100,000-year discharges are cyclical or 1,000-year discharges are cyclical. So we're getting information about the cosmos that we really couldn't get any other way. By the way, I should have really said this when this particular chart was bigger, but this is a good time to talk about this global warming nonsense. Notice, starting so at 1000 BC, we have a heating spike of about a degree or a degree and a half, and then we have another one at year 0, and another one at AD 1000. So every 1,000 years, so at 0 and at 1,000, we got this 1 or 1.5 degree rise. Now this particular chart stops at 1800. So what would you expect to have next? Well, we'd expect a 1 or 1.5 degree rise peaking in the year 2000, which is exactly what we got. So yes, indeed, there's been 2 centuries of global warming, and it's completely natural. Now, the next implication the third implication of the hypothesis is that ice ages are ended by an electrical energy spike, not a collision with an asteroid, not orbital variations, not volcanoes. It's an energy spike. Now, in the Ice Age, we have glaciers that are miles high, and they melt in less than 1,000 years. I mean, this chart is Vostok, and it looks like that's a steep spike, but actually, there's another chart which I unfortunately didn't include, and it shows that the northern hemisphere came out of the last ice age much quicker than the southern hemisphere did. If we stretch out the graph starting at 50,000, starting back here, and we bring in Greenland, suddenly this spike that looks so steep, it becomes a gradual ascent, and the one in Greenland is really steep. So like the glaciers melted in less than 1,000 years. Now how much electrical energy would it take to melt the glaciers in such a short time? So what we have then is the interglacial spike is rising intensity for centuries. And that's what melts the glaciers. But what would that mean for the rest of what effect could that have on the rest of the solar system and the other planets? That intense amount of energy. So what we're getting is a constantly increasing potential in the heliosphere. So that the potential difference between the sun and the heliopause is rising. That potential difference is rising for centuries. So what could that lead to? Well, the first thing that's going to happen is there's going to be extreme planetary weather events, because, I mean, now we have 250,000 volt difference, and we're now at the quiescent top of the spike. But while that spike was rising, then that potential gradient between the ionosphere and the surface is going to be always rising. So you're going to have amazingly powerful weather events. Now, we also know from the electric model that planetary spacing is electrically determined. And I mean, just this morning, Wall was telling us that if you had twice the voltage gradient, the planets would be twice as far. So we're going to get planetary orbits are going to be shifted. And we're going to have violent interplanetary discharges. So what we're going to have for centuries then is, oops, let's go back. We're going to have the thunderbolts of the gods going on for centuries, every 100,000 years. So now obviously this is different than what the Saturn capture hypothesis says right now. And it would be really good if we could somehow reconcile the ice core record with the Saturn capture hypothesis. And conceivably that could be done if this huge spike, which ends the ice age, what if it turned Saturn temporarily into a brown dwarf? See? Now, of course, I'm totally speculating here, and I'm way over my head on what's possible. But I can't, it's not easy to just dismiss the ice core record, because there are other temperature records, like for instance in the Caribbean, you can look back at temperatures based on what kind of seashells were being deposited and what kind of species could survive at what temperature. So there are corroborations for the ice core record. We can't just totally dismiss it. And we certainly can't dismiss all the wonderful things that Davis and others have discovered. So it'd be nice if those two things could be reconciled. Anyway, to summarize, we not only have a pulsating universe, we have a rhythmically pulsating universe, because the spikes are always occurring in cycles. So climate is Gaia dancing to cosmic rhythms. And the last slide is if we compare the interglacial temperature record to a clip of Irish music, we can see that these discharge events that cause these spikes, those are the instruments of the cosmic orchestra. So, thank you very much.